10 minutes break are up. Right. Let me see where we are. We are here. So we enter the next section, section 4, which is about solving equations. So most of the things we have done so far is just like setting up things, all right? Not even really working with them, or maybe except checking the normalization condition of the three-dimensional probability distribution. Now, solving equations, I uploaded the slides to Cyber University, so you should have something that looks like this, right? You have also my Jupyter notebooks that look like this. Right. Okay, so what to do in most things. So why do we solve equations? Well, that's a very good question, right? Why do we solve equations? What are you second year undergraduate students, right? And the second year is ending for you, so you're almost third year students. Can anybody tell me why you solve or why we solve equations? Why equations need to be solved? That's a weird question, huh? It's like you solve equations all the time, but can you tell me actually why? Yes, what is this key point?
Make the system keep
Okay. So it is, we want to find some value that expresses basically when some external conditions are fulfilled, right? Like when we have a linear equation, we normally want to have, what do we actually want to have? So we have a linear equation like this. And which point is the solution? Yes, the crossing through the x-axis, right? Why not the crossing through the y-axis? But because our variable is x, right? In this form of equation. So this is, so there are a few things I should mention here, right? One is, yes, we solve equations, but we solve equations to find conditions that, well, let's say that we find our variable to match some conditions. It's normally either no solution, one solution, or several solution. If we have a linear equation, we just have one. Now, the solution per se is often defined as intersection. Intersection means crossing. Like you at a crossroad, right, and you have a traffic light with your scooter, because two roads have an intersection. That's a crossing. And remember, x is our variable, and the y value just gives basically a shift here, right? The mx plus 1. Now, solving equations, yes, gives us some external conditions, for example, in a linear equation, but it also can put two equations into perspective. The difficulties we often have is to take our problems that we face in reality and translate them into mathematical expressions and solve that. The standard problem is always like the system of equations, where, for example, student A buys a chemical benzene for 100 NTD. Student B buys 50 grams of benzene and 10 grams of naphthalene for so many NTD, right? And student C does something else with the money. And the question is, how much does 1 gram of benzene and whatever cost? That forms the system of linear equations. We see that later. There's normally an exercise to that. Well, and if we are clever enough to formulate our problem into equations, solving them gives us, well, the conditions, right? And here the condition would be how much 1 gram of a certain chemical cost. So what do? We want to use SymPy to solve equations. We will look into setting up our equations, how to solve linear equations, how to solve systems of linear equations. That was the example I just mentioned to you. And we will have a discussion on numerical stability. When our systems of linear equations provide reliable solutions, and when certain conditioning of the system of linear equation lets us wonder if our solutions are that reliable. Okay, so what do? Equation solving is a fundamental part of mathematics with application in nearly every branch of science. Now you guys are material scientists, right? When do material scientists normally see equations? Have you seen equations so far in your education that have to do with materials?
Yeah.
Very good. Which one? Yes, we have a lot of equations in defect. Strain fields. We have the whole theory of defects, line defects that come, for example, through the, have you heard about the Volterra construct? The one you use, it's a cylindrical representation of a screw dislocation that is the start to derive the strain and stress field. No, yes? You should have thought of. Anyhow, so, and how did you solve them? You normally set them equal something, another condition, and then you see when that condition is true, right? Fulfilled. A root, now this is EMI. Everybody pay attention. No, not everybody. So a root, not a square root, a root for a function corresponds to its solution. So when I ask you to give me the root of a function, I want to know this point. If you write me the square root of the function, right? Square root and then function, this is wrong. Don't do this. So root and square root are very, very different. So far, so good? So I normally have something like this in the final exam, right? And then I have the students and I ask, give me the root of the function, write me numpy square root of that function. No. Okay, so be careful here. A root of a function corresponds to its solution, and the solution is this one here, right? The solution is the intersection with the x-axis. If we only have one function, if you have more than one function, is where the intersections of all the functions are. Note that square root and root of a function are not the same. So there's a sentence. To find the solution of a function, we want to find the position x where f of x equals 0. This means we want to find the crossing of x with the x-axis. So far, so good? Now there are several methods to find the root. For example, I can put in numbers, right, on the x-axis, and I can try to read the solution. That's called the graphical solution. So when you have a function, right, you always can plot it and then try to read the root of a function from the graph. That's okay, that's allowed, that's a valid method. Let's see what we have here. Okay, so can you tell me where's the root here? First question, which function? Let's say the blue one. Where are the roots? I know it's too easy, right? But the root are at 0, are pi and minus pi. So far, so good. And now when I ask you, hey, where are the roots for the orange curve? Oh, that has only one root at x equals 0, right? Okay, so you know roots and you're experts for roots now. So what we want to do next is, instead of a graphic solution, try to use SymPy to tell us where is the root. What we can use in SymPy is the solve method. So SymPy, f is the function, and x is the symbol where we want to find the root for. Quite simple syntax, no? Here's an example. X and y are SymPy symbols x and y. I define f equal x minus 2. And I ask SymPy, what's f? Well, f is x minus 2. Now I plot the function. So SymPy plot f. This is my function. You see, this plotting is a little bit different. Instead of sp.plotting.plot, I just use sp.plot, also works. And again, I can read the root from this graph. Right? Looks like x equal 2 is here the root. x2 is the solution. Good. Now I try SymPy solve. I provide the function. The standard variable it takes is x already. So it knows I am asking for the root, and it tells me the root is at 2. So far, so good. It's a very easy example. It's the sanity check. Everything still seems to work. So we can proceed. So note that function can have more than one root value, but also no root at all. I'll give you an example. We have two curves, x squared plus 1 and x squared minus 1. And you see the red curve has no intersection with the x-axis. How do I know this? Because I know the smallest value of x squared can be found at its minimum. The minimum of x squared is at x equals 0. And the value of the minimum is 0. When I shift 0 1 unit up, I'm here somewhere, right? When I shift the minimum one value down, I'm here somewhere. And then I just have a quadratic function. So let's see. Right. So here I have an example, x squared plus 2x minus 3. So this is a quadratic equation shifted down by 3 units and slightly slanted towards increased x values. Right, so x squared is quadratic equation. A parabola minus 3 is shifted 3 units down. And 2x basically slants all x value towards increased x. So it's not quite symmetric around the y-axis. So when we plot this function again, we find two roots. Who can tell me what are the roots from this plot? A little bit harder to tell, right? Because what you probably would do is using the PQ formula, right? So P half plus minus P square fourth. Was it plus or minus Q? I always forget. Anyhow, now we have SymPy. So what we can do is, again, take this function and plug it into our, or use it to solve our problem. In the upper example, I demonstrate the use of a variable here. So 1 or 2 slides ago, we defined x and y as symbols. The first argument is the function to solve. The second one is the argument. And if your argument is not in the function, then your function obviously has no solution. So when you ask the function of x, or where is your intersection with the y-axis, here y is a variable, not the function axis, then it tells you, I don't know what you're talking about, there is no solution, sorry. But if you say, yes, the function f2 of x, tell me where this intersection with the x-axis, and again, x here is the variable, then it will tell you, I have an intersection at -3 and 1. So far, so good? Okay, so what do we do when the computer gives us a solution? We trust it blindly, right? No. No, you always validate. Even with your own solution, you always validate. Because there could be mistakes somewhere, right? You don't know what all the ways where things can go wrong. They normally do go wrong. Let me see. So import simple, define my symbols. Okay. So I define the function. Wait a little bit. Is this one on here? Power on? Okay. Not sure why it takes long. Is the video running? Should be running, right? It should be running. Good. So the students listening at home can listen. Audio is also there. Very good. It's still evaluating here something. I'm not really sure what's the difficulty here. Maybe I need to interrupt. I need to restart. Not sure. So try again. Import the modules. You see here the little star still executing. Still executing. Does it take so long for you as well, or is your laptop faster? Or your PC? It's faster, right? Not sure what's going wrong here today. It's like the... Okay, how about I push this, right? I push this, and then we wait until my computer is ready. You do the plot here, and then we have the quadratic formula. We do the plot. We find a solution. We find a solution. There's no solution. And then we validate. How do we validate? Well, we have defined a function f2, right? And Python tells us, hey, the solution is at -3. It's the intersection with the x-axis. So I just asked Python, oh, if this is your solution, then yeah, show me what is the function value at this position, is same as from x -1 plus 1. And I'm executing. Maybe I should close something. Getting a little bit. Maybe I need to restart my laptop. This is executed. Very good. Hanging over here. Not really sure what's the difficulty on x squared plus 2x plus -3. Okay, so you try to validate this. I still need to wait for my laptop. But what you should see is, of course, that the function value at -3 and the function value at +1 equals 0. And then you have validated that your values are correct. Let me see. Go down, go down. So -3 squared is 9. 9 plus -6 is 3. And 3 minus 3 is 0, right? So I validated now with my own head. Imagine that. And now 1. 1 square plus 2, 1 is 3, and 3 minus 3 is also 0. So looks like actually I can do... Oh, what's going on here? Mhm. Tells me add object is not callable. How about we do substitute x with 1? So again, very, very slow, but I validate it now like this. Okay. Substitute x with -3. So what's going on? So just now I couldn't call the function as a function. No problem. What I use instead is substitute. So when we have an equation, for example, f2, it's like really, really slow today. Do you see that? It's like when we use substitute, we can substitute any expression in our formulas with something else. For example, I can replace x with y. Again, take a long time. When I, however, replace a variable or symbol with a value, the value will be evaluated. And in this way, I can check an expression defined in SymPy that represents an equation for a given point. So far, so good. Something more funny actually would be replace x with y squared. Very good, right? We also can now substitute y squared with m or whatever, right? Okay. So far, so good. We go back to the slides. So we know how to solve equations in SymPy with the solve method. We know how we read the roots from SymPy now, and we know how we validate the roots. Next step is to introduce parameters into our equation. So parameters are basically number or numbers which are not yet specified. It's a little bit like, I think we had the discussion before, what is the difference between a variable and a parameter? So a variable you can change during an experiment, a parameter you just take as is. A little bit different from a constant, right? Because a constant you even can't change as a parameter. Okay, so how do we work with parameters in SymPy when solving equations? Well, first thing is we need to define parameters, here a, b, c. Then we form an expression using these parameters. Here we have ax squared plus bx plus c. And ask Python to solve this for x, and then we get a solution. Now, in the slides, for some reason, it always tells me I didn't define SymPy. It's over here. I can do this. But it should actually work. So what we have here is basically an ABC formula of the quadratic equation. There is one solution equation for this ABC style quadratic equation. Do you remember? Right. And Simple is smart enough to actually give you both possible solutions. Right, and this minus b plus minus square root of minus 4ac plus b squared divided by 2a. So far, so good. So Python knows the ABC formula. But then you can question, hey, if Python knows ABC formula, maybe it knows the PQ formula as well. How handy would that be? So what was it? X squared plus, do you remember what to do here? So in the PQ formula, where do you get the P and where do you get the Q from? X squared plus 2x minus 4. What is P? What is Q? Nobody? PQ formula? Too long ago. PQ, maybe like this? Have you seen this before? PQ formula, right? The number in front of the x term is P, and everything else that has no x in it will be Q. Yes, no, maybe? Maybe a factor of 2 here somewhere. P, yeah, it's okay. It's okay, yeah. Okay, so Python is smart enough to find the solution or to apply the ABC and the PQ formula, which is very good because now all your high school math has become very, very simple. Questions so far? All right, so what you should get until here is standard solutions are accessible to you in Simple. Right, and solving a quadratic equation, this is, what was the 5th grade, right? When did you solve a PQ quadratic equation the first time? 5th grade, right? 3rd grade. 8th grade. I think it was 5th grade for me. Okay. But it also knows ABC formula. So far, right? Python is or Simple at least as smart as your math in 8th grade. Later we will see that there will be some limitations. Right? So just because we have a computer doesn't mean anything can be solved. How you say it in English, everything and anything can be solved, but there are some limitations. Because somebody must have sat down and actually implemented it. Meaning, we give a problem to Python, it identifies the type of the problem and then applies a solver or a solution algorithm. So far, so good. Okay. So now we can go to this part. we are moving from one equation to two equations. Now, two equations also can form one common solution. And again, the solution is defined as point of intersection. So when I give you two equations, I'm normally interested what is the solution of one equation with respect to the other equation. I do not want to know what are their individual intersections with the x-axis. I want to know what is their common point. So far, so good? So example. So we define the symbol x. We apply x to two trigonometric functions, sp sine function and simpi cosine function. Python is very fast. Very good. So when I do sp.plot, what was it? Trigger 3.1. I get the sine function. If I plot sp.plot trigonometric function 2, which is wrong, function. There we go. Right. So they are not in the same plot. It's a little bit unfortunate. And so a little bit of imagination, we actually can put these two curves on top of each other, and then we would see they are not intersecting at all points. They are not intersecting at no point, but there are a few points in common where they do intersect. So we try to find their common points. So when we want to find their common points, how do we do that? I give you here a few options. I give you trigonometric 1 plus trigonometric 2 and trigonometric 1 minus trigonometric 2. What's the correct way to do this? So the question really comes from that understanding what is given and then trying to figure out how can I translate this into a discrete expression. So just now we have seen we have two plots, right? One is cosine and the other one is sine. So this one here is supposed to be my sine function. The other one is minus cosine, right? So yes, no, maybe. So I want to find their common points, right? So I need to bring them somehow together. So I have one function again sine and the other one minus cosine. So far, so good? Now, so no, this is not what I want. Draw. So when somebody tells you this is function 1 of x, and the other one is function 2 of x, what do you do to find the common solution? Well, you want to know where do they have this point in common, right? So what you do is, well, the value of that function 1 must be equal to that value on that function 2, right? But we are looking for the same position. So you set them actually equal. But now, right, when you remember simpy.solve, we need to give it one expression. So what we need to do is we need to take this and reform this into one common expression. How do we do this? Well, we can always subtract f2, right? Then we get f2 minus plus f1, both as a function of x, to be 0, right? And this we can call our new function g of x. And this will have intersections with the x-axis now, where the locations correspond to the positions of the intersections of both functions. So in this small plot here, right, you already can see that the first intersection is quite is probably somewhere shifted into minus x region, right? So let's see. We are back over here. So when we have trigonometric 1 minus trigonometric 2, we actually get the proper solution here. So far, so good? So remember, when you have more than one equation depending on one variable, you need to find the common expression. Let us try some things. So we work here. There's definitely more than one way of doing this. For example, we can reformulate f1, f2, right? So trigonometric 1, trigonometric 2, into a system of equation and then pass this to a solver. Let's see, does it work with two functions? It shouldn't. A little bit weird, no? Now we get two independent solutions, which is different from having the intersection of both functions. Do you know what this means here? X null and x pi. It's a list of dictionaries, right, where we have solutions of these functions individually, but not in common. So when you try to think working with equal signs here, right, see what happens. No solution because it's a Boolean expression here. Let's see that separately. It's false. The functions are not identical. If you use an equal, you overwrite the content on the right with the content on the left. So you redefine the value for trigonometric 1, so you can't do this either. So the only one is you need to do a little bit of math outside Python. And then you get the right solution. Now, why does this one here does not give you the right solution? Trigonometric 1 plus trigonometric 2. Because, we go here, because trigonometric 1 plus trigonometric 2 answers you the question when the opposite of f2 is equal f1, because then you have a plus. So you must be here a little bit careful. So far, so good. So Python can help you finding intersections of two functions and more. But be careful what you do, because you need to apply, for this example, a little bit of math outside Python. Right? And if your math outside Python is wrong, then you basically put garbage in and you get garbage out. Okay? Good. Now we can go to solving square systems of linear equations. So why square systems? Because we have as many variables as conditions to solve them. In the slides, when you see something like this, you can see what's on the slide by shifting the slide to the right, and then see a little bit more of it. Or you go back to my Jupyter notebook and see there. So let's see. We start this chapter by introducing, first of all, a problem. And the problem is linked to higher order terms. Higher order terms, however, are somewhat in contradiction to linear equations. So linear equations have terms of first order terms in x. For example, f of x equal x minus 3 is a linear equation. And we can have several terms of linear order in an equation. That still makes it a linear equation. If we encounter nonlinear terms, here for example f of x equal x squared minus arctangents of x. Do you know what's arctangents? Do you know what's the tangents? Arctangents is the inverse function of a tangents. So if you have arctangents of 0 is 0, right, then arctangents would invert the equation, take the output of tangents, and tell you what was the probably input of tangents. So how would you solve this equation here with pen and paper? A little bit difficult, right? Shall we try it together? Tell you a secret. If we fail, it's not I would say it's not important, but it's not like critical, right? So sometimes failing is actually expected. So again, so the handwriting is a little bit different than normal, because writing on the screen is always a little bit cumbersome. So this equation, what do? We say f of x equals 0, right? Therefore 0 equals x squared minus arc tangents of x. So what do we do to solve? We sort, right? X squared equal arctangents of x. Two options. We take the square root, right? Then we get x equal square root of arctangents of x. Or we take the tangents, right? Then tangents of x squared equal x. And now, what do? I don't know. Difficult here, right? It's like if I take the arctangents again, I get the x squared, but I'm left with the x tangents, arctangents. If I resolve the square root, then I have the square on the other side again. So whatever I do from here, yeah, that doesn't seem to be that straightforward. And the issue is some problems are just too difficult to be solved. So we can implement this function. We can plot here the arctangents, right? So the arctangents in SymPy is a tan, not arctan, a tan. Sorry, this we don't want to have yet. Sorry again. So what you can try is then put this problem into SymPy, right? And maybe you're like, hey, I can't solve it. Maybe SymPy can solve it. But SymPy will tell you, I don't know what to do. It's very, very tough problem. So yeah, nothing I can do there. So this is a function. Okay, so this is the plot. Now when I uncomment, please find me the solution for x squared minus SymPy arctangents x. It will tell you there is no solution. Nobody implemented an algorithm that can find a solution yet. So no algorithms are implemented to solve equation x squared minus arctangents x. Right? So if nobody implemented that algorithm for you, SymPy also doesn't know what to do. So now the big swing is what has this to do with this chapter? Well, we speak first into solving systems of linear equations because we can show there are some conditions that we can check so that we know there is at least one solution of my system of linear equations or there's no solution. And the algorithms are nicely implemented. Okay. This, however, is not given for non-linear equations. Right? So they are more difficult to solve, and if no algorithm was implemented for this particular non-linear equation, then SymPy doesn't know what to do, and you need to use your head again. Right? So linear equations, yes, can be done. There's linear algebra for this. There are rules and quite sophisticated solvers. For non-linear equation, there might be a little bit more work to be done. So what is a system of linear equations? So the general expression of a system of linear equations is given here. So what we see is a11, x1 plus a12, x2 plus a1n plus xn. So we have n variables in one line that form one equation. So all of this equals b, some coefficient. And we have a parameters. And how many of the a parameters do we have? N. So for each linear variable, we have one. So far, so good. So when we have many parameters and only one measurement, we basically can determine one of the parameters a and have n minus 1 parameters left. What we would like to do is determine all parameters. How many measurements do we need to determine all parameters? Well, we need to have at least n measurements when we have n number of parameters for n independent variables. However, this is not always given. Right? We could have, for example, a number of m, where m is the number of equations. if m is smaller than 1, sorry, if m is smaller than 1, then we have 0 and the measurement. If m is smaller than n, our system of linear equations is underdetermined. If m is larger than n, we have an overdetermined system. That is normally what we do in fitting setups, right? Or linear regression. If our system has the same number of parameters and measurements, then we have a determined system. Now, writing down a lot of equations is a little bit cumbersome, so we generally work with matrix form. So here we have a matrix of coefficients, A. Then we have a vector of variables, here x. And we have a vector B that are our coefficients. Right, and the very, very compact form is given here. A, B equal x. Ax equal B. Right, I see. Nope. Change the spec. Comes later. So let's see. Let's go back here. So what we now have is basically a matrix A times x equal B, right? So x is our variable vector. For which we want to find the solutions. However, x is somewhat incorporated into this equation with the multiplication of matrix A, right? So what we can do is we multiply the inverse of A from the left. Then we got A minus 1 times A times x equal B, right? Sorry, AX, sorry, AB. A minus 1 times B. Vector matrix, vector matrix, matrix. So far, so good? Now, a matrix times the inverse of a matrix should be the identity matrix, right? Then we get x vector equals A minus 1 times B. So finding our solutions that are an x is basically to invert the matrix A. So far, so good? Easy. Okay, so let's see what we do here. Right. So matrix A must be non-singular, because a singular matrix is a matrix whose determinant is 0. Right? But if the determinant is 0, we don't have a solution beyond the trivial solution. So A must be non-singular. So here's a question for you that you can think of. So when we, for example, have a 2x2 matrix, remember 2x2 matrix, and the determinant is 0. What is the inverse of that matrix? Yes, no, maybe. Do you remember? So there is one special formula. Right? So when we have a matrix, let's call it M, that is 2 by 2. And we want to form the inverse of M. Do you know what to do? So M equal A, B, C, D. Does it look familiar? So the question is, the inverse of M is then what? 1 divided by, and then you need to change a little bit the elements. Yes, no, maybe. Anyhow, so this is actually a good time for break. And after the break, we continue here, yes? Questions so far?